we will look at two lock-free data structures. And there are quite a few, I mean, there are few slides, but the main part will be source code and figures, drawings. Okay, so we will look at these things. First of all, why do we want to use lock-free data structures? Some terminology, and then comparing locking, lock-free, and transactional memory. And then the two data structures are lock-free stack and lock-free first in, first out queue. So, why should we think about using a lock-free data structure? Okay, suppose we have hundreds or thousands of threads, and then it may be the case that using locks will be too slow, since if all threads need sufficiently frequently wait for a certain lock, then it can make the program slow. Okay, so using locks can limit the scaling of a program. And whether that's an issue or not obviously depends on the program and the input. And another thing is that a way to avoid this scaling limitation is to make the locking more fine-grained. Just as an example, the first parallel operating systems could have one lock to protect the file subsystem. So only one program could do something serious or critical with any file. Okay, but they could do other things. So with maybe 4 CPUs, that was fine. And then with more CPUs and more parallelism, this lock would be limiting. Okay, so then it was added one lock per file, basically. It's called an inode. It doesn't matter why, but that's the name for a file in Mac OS and Linux terminology in Unix. So one can use fine-grained locking, okay? But then we may add locking to the virtual memory system, and locking in many places, and after a while it can become quite complex. So of course we can use Helgrind and Valgrind, but they detect things that actually happen during the execution, not that there cannot be a deadlock or there cannot be a data race in the program for any input. Okay, so locking may lead to complex and hard to find bugs. So basically the idea with the lock-free data structure is that we remove the traffic signals in the city and use autobahn or freeway, and just don't have to interact so much with other threads. Well, that's a simplification, because well, if we have a stack, not all threads can update the stack pointer at the same time. But it is still the idea that threads should not have to wait for each other too much, as with locks and traffic signals. Okay, so why then are locks bad? Or well, as I mentioned, they can be they can cause serialization in a program, and they can also make the program more complex. But if you have a thread that has taken a lock, which is with other threads waiting for it, then there can be unexpected delays. Okay, so what can happen? Well, a thread can be, the operating system kernel can decide that this thread should not run, but some other thread should run. And, well, it will fall asleep with the mutex locked. And wake up still locked after some time. Okay, and there can be interrupts. So say that the disk operation has completed, and or a network packet has arrived. So and these things can take time. I mean, they not only can take, but they do take time. And if the thread that was interrupted due to this had a mutex, then the other had to wait longer. Or we can get a page fault. Okay, these are the first here are the most severe, and the next alarming thing is a page fault. That means the data is not in the computer's memory; it's on the hard disk. Okay, so then it must be fetched from the disk. We can see the computer ROM as a cache for disk, since most programs many programs, they are not in the computer memory, but they are on the disk, and then when it's their turn to run, they are copied page by page. A page is, for instance, 4 kilobytes. Okay, and fetching something from the disk takes a lot of time. Okay, this is not in this course. Page fault is not either, so I will absolutely not ask for. I don't think not. Okay, I may ask why can a thread be delayed, and well, these reasons are good to know about, but it's not part of this course to explain what they really mean in detail. Absolutely not. So just have a vague, well, you decide on what you want to know, but just a simple explanation what it's all about. Okay, and this you can basically, I mean, page fault, that's quite elementary, that the data, all data is not in the computer memory because it doesn't fit, so it must be put somewhere else, and the disk is a suitable place to put it while it's not needed. Okay, a more complex thing is virtual memory, and that is not part of this course, but there is something called virtual memory, so that different processes can use the same address but not using exactly the same physical memory in the machine. So the programs really don't know which physical address is used, and there is a translation, and that is done, and that's how virtual memory works. If we have 16 gigabytes in the computer, we can have many more processes, so that the sum of the address usage, memory usage, would be far greater than this 16 gigabyte. And that's related, I mean, page fault handling is part of the virtual memory system. So the memory addresses are translated from these virtual memory addresses to the real memory addresses, or physical memory addresses. And to make this translation quicker, there is something called a translation loci table, which just contains virtual and physical page number, and they are looked up quickly. And this table is in the chip, and it's limited size, so if a translation doesn't fit, then it's removed, and when it's needed again, it will be a TLB fault, so it must be fetched, and that delays the program. Or we can get the cache miss. That sounds not so problematic, but that can take hundreds of clock cycles. Okay, so threads can be delayed in various ways. Oops, I think I skipped one page. Okay, so what is then the idea with lock-free data structures? It's to use atomic variables and let the different threads work on a data structure concurrently. without locking the data structure, but instead detecting if somebody else had modified the data before us. And if that happens, then we typically want to update some local variable to reflect the new knowledge about this data structure, and then try again. So the question then is, how can we detect such concurrent accesses? Well, that's why we have atomic variables, and there is a very important operation that was introduced for the IBM 370 that we will come to soon. But let's just recall how atomic variables work. So this int, it can be incremented by different threads, and it will be incremented by 1 each time. But just that we use an atomic int, I mean there can never be a data race when we use atomic variables, and the sum will be as expected. But just using an atomic variable does not result in this read, modify, write sequence that we are interested in. This read, modify, write, that's the atomic operation. We read the old value, add something or do something, and write it back as one atomic operation. Here we read the value, add 1, and write back the result. But that's not atomic. It just happens to be using an atomic variable. But there is no guarantee that this will be the same result as using this one. Okay, so for integers, it's sometimes possible to use atomic operations. I mean, if we use this so-called compound assignment or assignment operator. But if we want to do something for which there is no assignment operator, what can we do? Well, say that we want to compute a new value based on the previous value. What can we do then? Well, we can do almost like this, but not really. But this is the idea that we will come to. Okay, so we save the old value, and we compute a new value based on the old value, and then we store the new value in this atomic variable. Of course, this does not work. It's not atomic at all. But what we want to do is to save the new value if a is still equal to the old value. If that's the case, then we have modified a atomically. And fortunately, this function was, I mean, it's available in all relevant languages with different names. It's frequently also just written CAS or compare and swap, and it was introduced for an IBM machine system 370. This is from lecture 6, and it takes 3 parameters, pointers to the first 2, and then the new value that we want to write into the atomic variable. Okay, so this pointer points to an atomic variable, and this expected points to a non-atomic variable. And if they are the same, then the value is written to the pointer. This is obviously one atomic operation. And if it's not, then this expected is instead updated to the current value of the atomic variable. Okay, and this assumes that recall that this weak form, it may fail on some machines which include power and ARM, and then they return false regardless of whether they were the same, and the expected is not modified, and you have to use this one in a loop. There is a strong as well, which can be written, used without a loop, but it's usually slower. Okay, so how can we do this now? Well, we save the old value, compute the new value, and then do this atomic compare exchange weak. If A and old A are still the same, then new A is atomically written to A. So this is how to do this thing, but only if A is equal to old A. Okay, so how should we think about this? Well, one way is to, when we want to update an atomic variable and we require that it is still equal to some older value that it had, that we know it had, then we can think of it as, is it I who should modify this atomic variable now, or maybe somebody else has done it. Okay, so how can we know that no one else had modified this? Now you should take a break and think. Actually, well, it depends on the situation. If the int can only be incremented as a modification, then we can know that no one has modified it. Or only, if it is changing either always incremented or always decremented, monotonically. But if it can be incremented by one thread and then decremented by another thread, and then it's our turn to check if A is still equal to old A, we can have misunderstood the situation, because what we want when we do this is to check if they are still the same, or more specifically that A has not been modified in between, but A may have been incremented and decremented and now get the same value. If it's an int, perhaps it doesn't matter. But if it's a pointer, it can be disastrous. If we think that the pointer is still pointing to the previous value of this atomic variable, then we will see that in more detail when we come to the stack, what can happen. Okay, so this problem is called the ABA problem, and basically it's a variable that had a value and then some other value and then the previous value again. And then it's not obvious how we can know if this has happened, but we will see how we can do that. Okay, so some terminology. An algorithm is blocking if one thread can delay another thread. That means if we use a mutex, or a lock, then it's blocking. Since, the one that holds the mutex can block the others, especially if it suffers from these unexpected delays. And if that's not the case, then it's non-blocking. Okay, then we have two more terms here. Lock-free and wait-free. And wait-free is much more complicated to achieve. But let's look at lock-free, and that is what we'll look at for the stack and the queue. They are lock-free, they are not wait-free. And okay, so lock-free means that at least one thread can make progress in a finite number of steps. And that's not the case with blocking, because if the thread that holds the lock is preempted, then it's not a finite number. We have no idea how many clock cycles will pass. Okay, so with lock-free, an individual thread may have to wait, but the program makes some progress all the time. So it's always one thread that succeeds and leaves this data structure, and some other can continue. So that means if one thread is in this data structure and it is preempted, that doesn't block the others. The others don't have to wait due to, I mean, that thread has obviously have to wait, but the others are not concerned. They say just goodbye and continue. Well, I don't know what they say, but they are not concerned about this. Okay, wait free, that's even better, because then all the threads can make progress all the time in a finite number of steps. So no, okay, here it's not the finite number of steps because we don't know how many iterations there will be. So this is not wait free, but it's lock free. Okay. Oh, okay. So that's what I was just going to say. That this slide was non-blocking, since there is no lock and it's lock free. Yes, but it's not wait free. Okay. So let's now reflect on locking versus lock-free versus transactional memory. One way to see locking is that it is in some sense pessimistic. I mean, it takes actions to avoid disasters by assuming there will be contention. Maybe that's a very realistic assumption. So actually using locks is the best thing. Okay, but lock-free is more optimistic. It assumes that no one else is there, and if there is somebody else, then it is taken care of. And okay, so why don't we always use lock-free algorithms? There are two reasons. Lock-free using atomic variables can be slower than using normal variables protected by a lock. So if the data structure itself is complex and needs lots of memory accesses, and I mean, if the operation to do something with the data structure is complicated, then probably a lock may be a better choice, because using lots of atomic variables will by themselves make updating them slower. But what is more serious is lock-free algorithms are much more complex to implement than blocking algorithms. There are frequently new published research on how to do lock-free operations on a simple data structure that you learned the first year. And what does that tell us? It tells us that doing this lock-free algorithms it's non-trivial, and some say there are just one okay, Herb Sutter has a very good video talking about. Herb Sutter is one of I think he is the chairman of the C++ standardization committee, and according to him in this video, it's like 50 persons who are in the world who are really good at writing lock-free algorithms for C++ at least. So it's not a trivial thing to do. As you will see soon, there are some subtle things that can happen. Okay. So if we compare that with transactional memory, transactional memory obviously is also optimistic, but it's trivial compared to trivial to use compared to lock-free algorithms with atomic variables, since it's the hardware that checks if there were conflicting memory accesses. If you have already done the last lab, the C part of the last lab, you will probably think that why don't we switch to transactional memory immediately? So that is trivial to get correct, but it's not always the best, because there can be conflicts and the transactions can have to be restarted. So the performance optimization is more difficult with transactional memory. So all these three have their suitable use cases. Okay. And obviously, which one is most suitable? It depends on the algorithm and the input. But let's now look at stack and a queue.